So today I'll be going over the EEDG 6370 homework number 3 for the fall of 2024. And in this homework, we were going to use this Altera Cordic IP. So into this IP, we were going to give it 10 bits, and we are going to output 5 bits. The input has 7 fraction bits, and the output has 3 fraction bits. So basically what this does is it's going to take this input and use it as a means to traverse a unit circle, and the output is going to be the sine and cosine of that point where it's at on the unit circle. And what we're going to do is we are going to also have this set to 50 because we're driving it with a 50 megahertz clock. And when we get this, what we need to do is actually we need to go into the file, and we need to change it so this reset signal is actually the negative of what it is generated as, because otherwise it's always going to be in reset unless you hold that button. And when I say that button, I mean this file right here where we have pin definitions. So right here, this is the clock pin. These are the cosine pins for different LEDs, for 5 LEDs, and then we have 5 LEDs for the sine pins, output pins, and then these A pins are all going to the switches, which will control the input, and then you have this reset pin, which goes to a push button, and this push button is usually a 1 until it is pressed, in which case it drops down to 0. So when just using the 10 LEDs, all you need to do is you need to go in and create the SDC file where you name the clock, set it to 20 nanoseconds for the period, and then set the port to the clock, and derive the PLL and the clock uncertainty. And then you need to make that change, like I said, where you change this to not a reset, and you go to create a test bench for this because we're going to simulate it first. So basically you just instance the block. You won't have all that. It'll just be a reset, clock, CNS. And then also you can create an initial block where you'll go through some test vectors, and you can generate a clock with an always block. And I'll just show you what this looks like real quick. Okay, so now we're looking at the waveforms of the simulation. And so here we come out of reset. When we come out of reset, basically we're having offset as 0, so we're just looking at the like a 0-degree offset on the unit circle. And so at this point, the cosine is going to be maxed out and the sine is going to be zeroed out. So, and then what we do is we are feeding in just a shifted bit into this. So with each test, we're going to like double the offset that we have. So it starts off not really changing anything. There's not enough of an offset to change the value of sine or cosine. Until we get here to 16, an offset of 16. So at this point, we're going to see that our sine value actually changes to, this will represent like I think a 0.125. And then once we double that, it'll represent a 0.25. And then when we shift it, or when we double that, that'll represent a 0.5. And at this point, this cosine value also starts to change. So when you have these 3 bits asserted, so that would be a cosine value of 0.875, I believe. And then as we double that, the sine bit will continue to increase, whereas the cosine bits will continue to decrease. These are similar, so this is close to a 45-degree angle, not quite. And then when you get to 256, what you can see here is that this is basically around a 90-degree offset on the unit circle. So the cosine is going to be close to 0, and the sine is going to be close to 1. And then over here you can see that we actually, basically at this point, we're feeding in a negative sign, and then it's zeroed out. So basically we're feeding in a negative 0. So we're going to have like a 0-degree offset on the unit circle. And so you see the cosine is at 1 and the sine is at 0. So moving past the simulation, we are going to actually now program this onto the board, and I'm going to show you what that looks like in a video that I will play right now. So now we have this coded up, and what you can see is with all the switches in 0, the cosine bits display a positive 1. Okay, so basically this is going to be as close as you can get to a 45-degree phase shift. And now what I want to do is I want to make this so that this is a negative 45-degree phase shift. So what I'm going to do is I'm going to flip all the switches to be opposite, and then also toggle this switch. So 3 up, 2 down, and then the rest up. And so this should be about a negative 45-degree phase shift. I guess so this is about as close as you can get to a 45-degree phase shift. Okay, so after seeing that video, you can see that the LEDs are properly lighting up to display the values of sine and cosine. And what we're now going to do is we're going to discuss the implementation where we actually use the 7-segment display. And so this 7-segment display is right above the LEDs. There are 6 different 7-segment displays. And what we have here is we have code where we can enable the 7-segment display if we have this defined in the code. What that is going to do is it's going to change the outputs and inputs to include a toggle input where we will toggle between sine and cosine, and then it'll add these outputs to the hex displays, and we get rid of the outputs to the sine and cosine LEDs. And now in this, we're going to generate some other stuff. So when we define 7 segments display, we have to make these wires for CNS. We make a wire right here where we mux between CNS. We have a register right here where we register the value of either the sine or cosine. This register right here is the controller for the mux. Right here we have a debounce shift register that will debounce the input of the toggle switch. And what you can see right here is a timer. So I create this timer. It basically displays either sine or cosine for about 1/3 of a second each time you toggle. And then right here you can see I have basically created a wire where I have programmed the different 7-segment display values. Each of these corresponds to a number, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And also up here I have some define statements where I define a positive sign, negative sign, a COSINE, a blank, and then an underscore. And I use an underscore instead of a decimal point because the decimal point is not working on the 7-segment display. It's not wired up. And then here in the code, you can see that I mux the sine and cosine depending on the control bit. And then right here, I have an always block, and this is just resetting all the different registers. And then right here, so I register the input, and if it's a negative number, then I do a 2's complement. And then here in the code, I debounce the toggle switch. And right here, I use the input, the debounced input to toggle the switch. And then right here, this is for displaying the cosine or sine words. And then here we have the this is the actual assignments to the hex, the 7-segment displays to display either sine or cosine. And then if we're not in the displaying sine or cosine state, then here this assigns either a positive or negative sign. And the positive sign is actually just 0 because you can't really make a positive sign exactly on a 7-segment display. So I basically decided to leave it blank. And then in the ones place, so this is active if the value is either positive or -1. And then this is a decimal point. I just use an underscore to show a decimal point. And then right here in the tens place, and the hundredths place, and the thousandths place, I have to decode the last 3 bits to determine what value to give these. And then right here you can see it's just the instance of the Cordic IP. So also, when we make this change, we have to go into the QSF and we have to create the different pin assignments. So we assign all the 7-segment displays, and also we have to assign the pin for the toggle push button. And next, basically, I will just be cutting to a video showing this working, and I will show that right now. So here you can see that we have the 7-segment display version uploaded, and right here, so I have a reset toggle, and you can see that I flash, it's either sine or cosine. So if I toggle to cosine, it displays cosine, and then sine, cosine, sine, and that lasts about 1/3 of a second. And then what you can see here is that so when the sine is 0, the cosine is 1. So this is about a 0 degree phase shift. And then as I start to flip these, eventually the cosine starts to change. So right here, 0.875. Here, I expect to go down to maybe 0.75. So 0.5, and then let's do the negative of that. You can see it's also 0.5. But then if we look at the sine, so it's negative 0.875, and then let's go back. 0.875. So you can see that it goes from having a cos or something like this to something like this. Let's get it, yeah, about 0.75. So the cosine is 0.65 and the sine is 0.75. And then if we, so that's about a 45-degree angle, roughly speaking. So let's make this negative. Then add 1. So the cosine is 0.625, and the sine is still negative, or is now negative 0.75. So you can see that it's working properly.